An acid-base titration is a technique. It's a way of quantifying the amount of acid or base in a solution, and it utilizes solution stoichiometry. So what happens in a titration is we take a substance of known concentration and react it with another substance of unknown concentration, and we can find out what that unknown concentration is. A common acid-base reaction is hydrochloric acid with sodium hydroxide. I'm just waiting for my pointer to behave. So I'm not touching the iPad right now. I don't know what it's doing. There we go. The net ionic reaction is H plus OH minus, giving water. So let's look at what happens in a titration. So here we've got hydrochloric acid in solution. And we're only going to show the hydrogen ion here. We're not going to show the chloride ion. The chloride ion is a spectator. It just hangs around and it doesn't actually participate. So here we have an HCl solution, and so we've got these hydrogen ions in the flask. Then we're going to use our burettes, and the burettes are going to have sodium hydroxide in them. And again, we're not going to have the sodium ions in the pictures because they're just spectator ions and they don't participate in the reaction. So we can just pretend they're not there. So here are the hydroxide ions in the burette. As we add hydroxide to the hydrogen ions in the flask, that net ionic reaction occurs, and we have one hydroxide ion and one hydrogen ion, and they react to form one water molecule. And as we continue to add hydroxide ions, we react the hydrogen ions that are present in the flask. And what we want to get to is the point where we've added just enough hydroxide ions to neutralize all the hydrogen ions. Now we can't see what's going on here, and so we use an indicator so that we can visualize the equivalence point. The equivalence point is the point at which the moles of hydroxide ion are equal to the amount of hydrogen ions in the original sample, and then we say the titration is complete. So we use an indicator, which is a type of a dye, whose color depends on the acidity of the solution. And we're going to, phenolphthalein is a very common one. It's clear in acidic solution, colorless, and it turns fuchsia in basic solution. And so we can use that to tell us when we've added enough sodium hydroxide. Usually we have one concentration that we know precisely and the other one that is unknown. And by measuring the volume of each, we can figure out what the unknown concentration is using solution stoichiometry. So here are pictures of an actual titration. Sodium hydroxide in the burette looks like water. It doesn't act like water. HCl in the flask also looks like water. As we add sodium hydroxide, we initially see a little bit of pink where the sodium hydroxide is contacting the acid solution. And that's because it hasn't fully mixed yet. And so we see a little bit of excess sodium hydroxide right here until we swirl the flask and mix it. And then that pink color goes away because the solution is still acidic. And we keep adding and swirling until we add one drop and we swirl it, and the whole solution turns a pale pink. And that's what phenolphthalein does. It's got a lot of pHs and THs in it. And so when we reach this endpoint, we know that we've added an equal number of moles of hydroxide ion to the number of moles of hydrogen ion in the original flask. So let's do an example calculation. Titration of a 20 milliliter sample of H2SO4 requires 22.87 milliliters of 0.158 molar KOH to reach the equivalence point. What's the concentration of the H2SO4? Well, it's very helpful to have the balanced chemical equation. So H2SO4 plus, oh, not sodium, potassium hydroxide, all right, yeah. And when those are mixed in this neutralization reaction, what are the products? We're going to get water and salt. It's going to be the K plus and the SO4. So K plus and SO4, 2 minus. We need to look at the formulas for the ions with their charges so that we can predict what the formula is. It's K2SO4. Is this balanced? No, it isn't. Here I've got 1 potassium, and over here I have 2. So if I put 2 in front of KOH, that balances the potassiums. I've got SO4 and SO4, so those are okay. Here I've got H2O, I've got 2 hydrogens, and here I've got 2 hydrogens from that one and 2 hydrogens from this one, 4. So I need a 2 in front of the H2O. This acid, H2SO4, is called a diprotic acid because it has 2 acidic protons. So it's going to take 2 moles of hydroxide ion to neutralize 1 mole of this. So there's our chemical equation. We're going to approach this like it's stoichiometry because it is. So I'm going to take these numbers and write them under the equation. I have 20 milliliters of sulfuric acid, H2SO4. And then I'm told that we use 22.87 milliliters of the KOH, and that the concentration of the KOH was 0.158 moles per liter. What am I trying to find? The concentration, the molarity of the H2SO4. What do I need to calculate molarity? Molarity is moles per liter, right? They gave me the volume in milliliters. I need to figure out the number of moles. I can convert milliliters to liters. That's going to be equal to 0.0200 liters. So I could put that up here. But I need to find the number of moles. Oh, that's just not going to work very well. 0.0200 liters. I need the number of moles. I can take, using solution stoichiometry, I can take this volume of KOH and convert it to moles of KOH and then convert it to moles of sulfuric acid. That's what I want to have happen here. So I'm going to take liters of KOH to moles of KOH to moles of H2SO4. And that's what I'm going to plug in up here to calculate the molarity of the solution. Is he done? The train? Any questions? So I'm going to start with this volume. I'm going to convert that to from milliliters to liters. So that's going to be 0.02237. And if you're still having problems with that, come see me and I can show you how to do that again. It is 8.7. Yes, I misread my own sloppy handwriting. So I'll just... There, yeah, it was an 8 all along. Thank you. So liters to moles of KOH in these equations, it's important to have moles of what? Because otherwise you can end up with your numbers in the wrong place, which leads to incorrect answers. So liters to moles, and then I want liters of KOH down here, and moles of KOH down here, so that my units cancel out. Such a useful thing. This concentration that I was given for the KOH is the relationship between moles and liters. So it's 0.158 moles per liter. And the mole-to-mole ratio comes from the balanced chemical equation. 1 H2SO4 to 2 KOHs. 1 to 2. Sometimes people want to use that dilution equation, M1V1 equals M2V2, and you might run into a tutor that shows you how to do it that way. Don't do it. On one like this, where it's not a 1-to-1 ratio, it won't work. And so it's a very bad habit to get started in, so just avoid that. Think of it as stoichiometry. 0.02287 times 0.158 divided by 2. Well, that's not right. I'm having issues with my calculator. So my calculator is showing me 0.0018067. How many significant figures should this number have? 3. This volume had 4. The concentration had 3. So remember, those leading zeros don't count. 00180. This is that 0 is the last significant figure. So that's moles. I'm going to keep that 6 and 7 around when I bring it up here and put it into this equation. 0.0018067. Underlining the 0. Ran out of room. So I'm reminding myself there's 3 significant figures in the numerator, and there's 3 in the denominator. So 0.0018067 divided by 0.02. And that's going to be equal to, I'm going to round to 3 sig figs now, 0.903 molar. That's the concentration of the sulfuric acid solution. Any questions?